Hello and welcome to Physics Problems One by One. So here is a problem. As always, read it, maybe once, maybe twice, and then pause the video and try to solve it yourself. Today's problem is part 2 of the previous problem. Remember, the bicycle moves with a constant speed, starts at point A, starts with the speed v0, and moves forward, and then the car catches, accelerating with a constant acceleration, and at some point it catches up, and this is the point when it catches up, and we need to know what is the relation between the speed of the car at that moment and the speed of the bicycle, and we come up with v equal to v0. First of all, one thing, just looking on this, I want to emphasize how we calculated. This is a graph of v versus t, and I just trying to bring it to the point that the area underneath the graph of velocity is the distance that body covers, and since they are located at the same point, they cover the same distance. That means the area under this graph should be equal to the area under this graph. And indeed it is true for these values, because indeed if we say that this time, for example, is t, last time I just convinced you that this is the case, just looking on those areas and saying that this triangle is the same like this. But this time we can also, I forgot to mention another way of proving the same thing, that this area of this triangle is v0t, right? This is the height, this is the side, this multiplied by this is the area of this triangle. This rectangle, sorry. This rectangle is v0t. And then we look on this triangle, and on this triangle what we see is that this is t, and this is height, and height is double, and we multiply this and divide by 2, because this is triangle. This is S, and I put a triangle, and this is S, and I put rectangular. And those areas are the same, and obviously they are, because 2 is cancelled out, and we have v0t and v0t, and this is only in the case when this is twice big as v0, that's why I put it to 0. Okay, anyway, that was the problem, and today they're asking us, me, I'm talking about me as if me is they, but yeah. Also to build the graph of the distance, because obviously requires some water, but for now this will do. So I will put two graphs. One would be the graph v over t, and again this would be time when they meet, and this would be the car that accelerates. That's why v equals v0 plus at, and v0 is 0, and the bicycle moves like this, so it's v0, and this distance is double that, and that's the graph of v. But we may be interested only in the graph of x. If we put here x, and this is acceleration, we may be interested in the graph, not v versus t, but x versus t. Okay, so it's very simple for the car. Car moves with a constant speed, and we know that for the constant speed, the x grows, and this is the same point. That's why I put one graph under the other. This is the point when the car reaches this point. And this is because this x equal vt at any moment, at any particular moment, this is valid when t equals 0, when t equals this, when t equals this, and when t equals t. Capital the point, the time when they meet. Okay, but for the cars that moves with acceleration, x equal v0 equals 0, so the only thing we have at squared over 2. So this is the graph of parabola, and this parabola starts with a tangent, with initial, which is the speed. It's 0, so it goes, and now it goes like here. So it's very interesting this point. What is happening at this point? First of all, it goes and it comes, and this is x. It is the same d at the same point t, because they are located, they covered the same distance d, and they are located at the same time at the same spot. And let me put here this. So this indicates that this graph, this parabola, is x equal at squared over 2. So now back to the point. This is a middle of this time period, and at that middle of the time period, the car still behind. It's like this area, the area that covered by car, and we see that it is half of the area covered by the bicycle. The bicycle is way ahead, so the bicycle already covered the half of the distance, d over t, and the car covered only this point, would be d over 4, the half of this. So the car covered half of the distance that bicycle has covered, and bicycle was moving all the time faster. And why we know that it's faster? Because v at any point was bigger for the bicycle than for the car. Finally, car accelerated to the point that the speed is the same, and now car starts to catch up. And this is exactly what we see, by the way, on this graph. Because remember, if we have x over t, and no matter what the graph, if we put this slope, this incline, this alpha, we can always say that at this particular moment, tangent alpha equal v. So v always changes, the slope of this graph is always changes, but in that particular moment, they are parallel. They are parallel, that means that they meet with, they go with the same speed. And then the car speed increases, and this is the point where they meet. And at that point, I just want to make it a little bit more room for that. I don't need this, I don't need that. And if I draw the slope of the bicycle, it would be this. But if I draw the slope of the car, it would be this. So if this is alpha and this is beta, I can say that tangent alpha is equal v0, and tangent beta is equal to v0. Let me remove this. Is equal to v0. And that's basically all that we can tell about those graphs. That's all they ask us. So, part 2 is over. There will be part 3 and part 4. Meantime, subscribe, bell, like, comment, question, your problem, put it in the comment. If it's an interesting problem, I gladly will solve it for you and put it online. Thank you.